A statement from teacher Carlos. Focusing on Durham School, I've committed my entire calling to empowering an unequivocal hypothesis about the universe. Then this happens. The theory is being scrutinized. I embrace this challenge because it is through such inquiry that we advance and make strides in science. The James Webb Space Telescope is fundamentally disrupting several widely held beliefs in cosmology that have been considered truth for a long time. A new ultra-deep image has revealed that we have made significant errors in astronomy. The telescope, which was designed to reveal the earliest stars of the universe, is proving to be truly groundbreaking. The past perspective could now give rise to an entirely new factual outlook. Not all experts are troubled by these revelations. Many are welcoming these advancements, as it has long been evident that there were flaws in our previous theories. The anomalies in observing the universe's rate of expansion alone should have raised concerns long ago. However, instead of critically addressing these red flags, many adhered to outdated theories. The cosmic microwave background radiation, CMB, the oldest light in the universe, was created approximately 380,000 years after the Big Bang, when the universe had sufficiently cooled for electrons and protons to form stable hydrogen atoms. This chain reaction, known as reionization, made the universe transparent to light. The CMB was first detected in 1964 by American physicists Arno Penzias and Robert Wilson while they were working on new radio antenna technology. They encountered a persistent noise coming from every direction. This discovery was initially thought to be strong evidence for the Big Bang theory of the universe's origin. Penzias and Wilson were awarded the Nobel Prize, and their findings became a cornerstone in the history of space science. The CMB undoubtedly provides a brief glimpse into the early universe, with minute temperature fluctuations offering crucial insights into conditions shortly after the Big Bang. Scientists have used the CMB as a reliable benchmark to measure significant aspects of the material universe, including its expansion rate. Edwin Hubble had already made such calculations in the late 1920s. He observed that distant galaxies were moving away from us and that their velocity was proportional to their distance, a relationship now known as the Hubble law or the Hubble constant. Although Hubble's measurements were not as precise as those made today, they were groundbreaking at the time. When the CMB was discovered, scientists recalculated the expansion rate and found it to be significantly lower than Hubble's original estimate. Later recalculations, using type Ia supernovae as standard candles, provided a higher estimate. However, discrepancies remained, and the inconsistency in expansion rate measurements has been recognized since the 1990s. Researchers have hypothesized that there might be issues with CMB data analysis methods or with the nature of general relativity itself. This inconsistency, known as the S8 tension or Hubble tension, suggests that our understanding of the universe might be fundamentally flawed. Since the James Webb Space Telescope, JWST, began its operations, it has delivered remarkable data that could help address this issue. Galaxies so old and mature that their formation may theoretically have begun before the Big Bang are challenging established cosmological theories. Astronomy now faces what is considered the greatest crisis in modern cosmology. The universe's rate of expansion and the theory of its origin are under intense scrutiny. New images reveal a cosmos that fundamentally differs from previous models. The S8 tension has served as an early warning for researchers who continue to adhere to outdated theories, now grappling with evidence that our understanding of the universe might be incomplete. This shortcoming has left many researchers disheartened and unsettled. To address this crisis, we must recognize how science functions. Theoretical scientists use a combination of mathematical models, observational data, and logical reasoning to draw conclusions. Their understanding comes from observing patterns, analyzing test results, and conducting theoretical assessments. The term theory itself signifies a progression of ideas and hypotheses rather than absolute truths. Teacher Carlos elaborates further. This crisis presents not only challenges but also opportunities for growth. As we confront the possibility that our foundational theories may be flawed, we open the door to revolutionary discoveries. The James Webb Space Telescope has become a beacon of scientific inquiry, inviting us to re-examine long-held assumptions. Among the most striking findings are galaxies that appear far older and more evolved than current models predict. These observations suggest that either our understanding of cosmic timelines is incomplete or that fundamental aspects of physics, perhaps even the nature of time itself, require re-evaluation. One of the key questions now facing cosmologists is whether these anomalies represent isolated phenomena or point to a more systemic issue with our interpretations of data. Could there be undiscovered processes influencing the formation and evolution of galaxies? Are there unknown variables that disrupt the neat equations of general relativity and quantum mechanics? This moment in science calls for humility and collaboration. Theories are not static truths but evolving frameworks built on the best evidence available. As new data emerges, scientists must adapt and refine their models, no matter how unsettling it may be to discard cherished ideas. The pursuit of truth demands it. However, skepticism also plays a vital role. While the James Webb Space Telescope provides unparalleled clarity, its data must be rigorously analyzed and corroborated. The scientific community must guard against drawing premature conclusions, as history has shown the dangers of overconfidence in new discoveries. The implications of this new era in cosmology are profound. Beyond reshaping our understanding of the universe's origins and structure, it challenges us to reconsider humanity's place within it. If the cosmos is more complex and dynamic than previously imagined, what does that mean for our future exploration and stewardship of the universe? As students and researchers, we must embrace the unknown with curiosity and determination. Science is not a pursuit of certainty but of understanding, a journey into the vast, uncharted realms of existence. The James Webb Space Telescope has reminded us of this, revealing a universe more intricate and awe-inspiring than we ever dared to dream. Our shrewd information comes from pictures given by telescopes, sound waves, and radiation caught by radio telescopes, as well as information from neutrino and gravitational wave identifiers. The James Webb Space Telescope allows us to confine the most spread-out light into individual frequencies and examine it in magnificent detail. It can show which elements were present in massive structures billions of years ago, the mass contained within them, and the number of stars present. However, Webb's photographs may have limitations. For instance, it can't easily distinguish structures or faint objects, such as black holes, that produce similar brightness due to gravitational lensing. Our perception has advanced to consider various possibilities as pieces of understanding, often dismissing alternative explanations. New discoveries from the James Webb Telescope offer critical insights that could lead to replacing old theories with new data. Researchers are now wrestling with these findings, which seem so remarkable that uncovering new explanations is proving challenging. The latest discoveries are shaking the foundations of established science, causing concern among various specialists. The physical science rules that dominate today are still significantly influenced by Isaac Newton's 17th-century work. For a long time, his laws of motion and gravity provided the foundation for understanding the real world and the universe. Newton's laws work admirably under typical conditions on Earth. However, in space, his ideas required extension to an unimaginable degree, as achieved by Albert Einstein in the 20th century. Einstein's special theory of relativity, published in 1905, transformed how we interpret reality, showing that the laws of physics depend on the observer's movement. His general theory of relativity, published in 1915, extended these ideas with mathematical predictions of gravitational phenomena, based on the curvature of spacetime caused by masses like stars or galaxies. While Einstein's theories were groundbreaking, he recognized their limitations and sought a unifying framework, an endeavor that remains unresolved. It is fascinating to consider where errors might lie. Michio Kaku, a prominent American astrophysicist, suggested that solving this issue could lead to a Nobel Prize. We need to explore whether our understanding of reality has been flawed, whether there have been misinterpretations of observations, or if telescopes themselves might be at fault. Dark matter and dark energy are key suspects in the cosmological crisis. Current models suggest that dark matter and dark energy together account for about 95% of the universe, yet neither has been conclusively observed or proven to exist. They may not exist at all or may possess properties we do not yet understand. One possibility being studied is that dark matter's properties could have evolved over time, potentially offering insights into gravity, which should interact through mass or spacetime. Gravity has not been conclusively shown to behave as expected. However, the reality of spacetime curvature, as proposed by Einstein, has been confirmed multiple times. We cannot entirely rule out the possibility that gravity has unexpected properties or that another phenomenon is influencing gravitational interactions over time. Certain constants in cosmology and astronomy have been established as central truths, largely due to their consistency. Studies suggest that slight variations in these constants could provide new insights into the universe, potentially explaining phenomena without the need for dark energy. It is also possible that our understanding of light behavior has been flawed, leading to inaccurate distance estimates and overstated galaxy ages. Perhaps our assumptions about the universe's origins were incorrect, or we misinterpreted the cosmic microwave background radiation. It may even be that the universe did not originate from a single starting point, challenging the Big Bang theory. Small errors in the Webb telescope or other observational devices cannot be ruled out. Some experts acknowledge that mistakes in instrumentation, data processing, or interpretation are always possible. The ongoing reassessment of cosmological theories highlights the essential nature of scientific progress, the ability to adapt and evolve our understanding based on new evidence. The James Webb Space Telescope's observations are more than an innovative leap. They represent a pivotal moment in our journey to unravel the universe's secrets. As we grapple with these discoveries, it is crucial to recognize the broader context and implications of such profound shifts in cosmology. The process often requires refining theories to align with new insights. The discovery of anomalies or contradictions in established theories can be unsettling, yet it also presents a critical opportunity for scientific advancement. Theoretical models in cosmology are designed to provide a coherent framework for understanding the universe's origins, evolution, and dynamics. However, as new data emerges, these models must be tested and, if necessary, revised to incorporate new insights. A critical area of focus is the nature of dark matter and dark energy, which are central to contemporary cosmological models. Dark matter, an elusive form of matter that neither emits nor absorbs light, was proposed to account for discrepancies between observed galaxy rotations and the mass inferred from visible matter alone. Dark energy, on the other hand, was introduced to explain the observed accelerated expansion of the universe. Despite their pivotal roles in current models, both dark matter and dark energy remain enigmatic, with experiments on Earth failing to conclusively detect them thus far. This has led researchers to explore alternative theories and possible explanations. The challenge of understanding dark matter and dark energy is compounded by the vast scales involved in cosmological studies and the observation of distant galaxies. The cosmic microwave background radiation and other remarkable features provide indirect evidence of these components, yet their elusive nature remains a puzzle. This uncertainty has prompted scientists to consider a range of hypotheses, from modifications to existing models to entirely new laws of physics. Some theories propose that dark matter could be composed of unexpectedly exotic particles, or that dark energy could represent a new fundamental force. Another fascinating area of cosmological study is the examination of cosmic inflation. This theory suggests that the universe underwent rapid expansion in its earliest moments, leading to the large-scale structure we observe today. While inflationary theory has successfully explained various aspects of the universe, such as its homogeneity and flatness, it also raises questions about the nature of the inflationary period itself. Observations that challenge established models of inflation could lead to revisions in how we interpret the universe's early history. Finally, the search for extraterrestrial life remains a driving force in space exploration. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened new avenues for studying the conditions necessary for life. Advances in telescope technology, such as the James Webb Space Telescope, allow us to investigate the atmospheres of these exoplanets for potential biomarkers. The possibility of finding life beyond Earth carries profound implications for how we understand the universe and our place within it. In conclusion, the reassessment of cosmological theories is a testament to the strength of the scientific method. The James Webb Space Telescope and other advanced instruments have provided astonishing insights into the universe, prompting researchers to revisit and refine established theories. This process of continual inquiry and correction is essential for advancing our understanding of the universe and addressing the fundamental questions at the heart of cosmology and astronomy. As we continue to explore the cosmos, we remain engaged in a quest for knowledge that not only seeks answers to key questions but also inspires future generations to push the boundaries of human understanding.